Hey everybody, thanks so much for joining our talk on gamification and reinforcement learning in practice. This research was authored by Paul Swenson and myself, Anish Patel, and advised by David Stroud and Jules Stacy. So let's talk about gamification. What is a game? A game is any activity that has rules and involves any combination of chance, knowledge, and skills. The objective is to win against other players or solve a problem. So, can anything be a game? When we look at gamification, we set any problem into the context of a game. We incorporate elements of a game into non-game contexts, such as a business problem. For example, in marketing, when we can look at different ads, we want to see which ones attract the most customers. We define the rules of the scenario, and points or reward systems are established on which the ads will be judged. Ultimately, we pick the winning ads. If a problem is framed in a way where points are earned by taking actions, it can be put into a reinforcement learning process. Today, nearly all games utilize some type of artificial intelligence when playing versus a computer. Some AI are even better than superhuman. For example, AlphaGo is a reinforcement learning algorithm that was created by DeepMind, a subsidiary of Google, which was able to defeat the world champion. At the time, very few people thought this would be possible. So let's dive into what reinforcement learning is. There are a few key terms that we need to understand. First, the agent. That refers to the model or algorithm that learns to complete a particular task. Secondly, it's important to understand the concept of the environment. The agent learns by interacting with the environment. Third is the action. The action is any way in which the agent interacts with the environment. Fourth is the state. The state describes the current situation that the agent is in. Lastly, and very importantly, is the concept of the reward. This describes how the agent should behave in an optimal scenario. Suppose the agent is a self-driving car. In this case, the environment would be the road and everything that goes along with the roads, the stoplights, the signs, the people or animals that may cross the road, and everything that surrounds the road. The actions the agent or the car can take are turning, braking, accelerating are some examples. And the state can be described as the current position of the car within the environment. And then the reward function in this case would have some sort of function where we get positive points, maybe for staying in the road, centered in the road, following traffic lights, following the rules of the road. And then we would get different negative rewards, for example, veering off the road, staying more from the center of the lane, or hitting any object for incorrectly following any road rules. So let's move over to what we're talking about in our research project. We focus mainly around GDP and the output gap. What is GDP? It more or less describes everything in a country's economy, the value of all goods or services produced by a country. And what's the output gap? The output gap measures the difference between the actual GDP and the potential GDP. The potential GDP being what the country is potentially capable of producing when it is most efficient. So why should we really care about this? We care because the gap tells us if the economy is producing above or below what is most efficient. Neither scenario is optimal, and resources are either being over or underutilized, respectively. If a bank can successfully predict the economic position of the country they operate in, they have a significant advantage in determining investment risks against their competitors. For this project, we utilized data from the Federal Reserve Economic Data Source, FRED, which is publicly available. Now I'm going to go ahead and turn it over to Paul for a deeper dive into the details of our project.
Thanks, Anish. So now the question is, since we have the data, how do we turn it into a reinforcement learning framework? That is, how do we turn it into an environment? You see on the right side, we kind of have this Markov decision process that's just a fancy way of describing the states that an environment can be in and how you transition between them. And what we want to do is we want to take the data and convert it into that format. So we have each of these columns, all the rows associated with them, and we want to turn it into a state with an action taken by an agent to transition to the next state. The state at the current time is equal to the first row in our data set. You can see it matches up here. And the state at t+1, so the state of the future time, is going to be equal to the following row. So just like in a regular data set, a regular time series data set, we have a series of observations over time where the values will change. So we just keep repeating this process over and over again until we reach the end of our data set, and then our environment will restart to the beginning. Here we have the reward function. The reward function defines what the agent gets. So in this case, our reward is made up of 3 components. The first component is this 0.01. That's just a constant, and that's going to scale the residual between 0 and 100. Then we take that residual, multiply it by this constant value 0.01 to scale it, and then at the end we add 100. And what this will do is this makes our reward have a constant slope, which helps the agent learn good actions versus bad actions. If it takes a good action, it gets a larger reward. If it takes a worse action, it gets a smaller reward. Here we bounded the actions that an agent can take between negative 10,000 and positive 10,000. And this 10,000 represents billions of US dollars. That's the predicted output gap. Unfortunately for us, our results were not very good. Over time, the agents predicted worse and worse. So how to interpret this is that the mean reward over 20,000 steps is about 500 points. If we remember from earlier, the maximum reward at any given step is 100 points. Whereas here, the reward sits at 500. On average, our SAC 8 policy earned about 3 points per step. So even though our models didn't perform very well, you can see that there is a clear use case for taking existing data problems and converting them into a reinforcement learning problem. Just because in our case, our reinforcement learning agents weren't able to successfully predict the output gap, that doesn't mean that other data sets couldn't be successful. And it could open your eyes to some new applications and new techniques for machine learning in spaces that you might not expect. This could be a good alternative for just plugging in your usual decision tree models or linear regression models. Any questions?